Hey everybody, and welcome back to Algebra 2 Online. So the plan for today is actually to just get a little bit better understanding of how logs really work and what they really are. So one way that I've just sort of talked about them is that they're just the inverses to exponentials, right? And so you can kind of use this to help evaluate things like this. We would read this log base 2 of 8, and that should be the inverse to a like 2 to the x graph, and that is actually this red graph right here. This is 2 to the x. You can kind of see it because if you'd like do 2 to the here this is the one I want to show 1, right? 2 to the 1 is 2, right? 2 squared is 4. 2 to the third is 8, and so on. And so this one down here is log base 2, or log base 2. Yeah, I should just say log base 2 of x. And so it is the inverse function of 2 to the x. And so if you wanted to know what you get out of this log when you plug in 8, you can just look at the inverse sort of to go there, right? So what do you plug into this to get out 8, right? Because the input here is going to be the output here. And so that's kind of how I think about it. So if you go up here to 8, right? We just sort of set up 2 seconds ago, but we know that is 3. And so 3 should be the answer, and it is the answer. So I'll just sort of show you here. If you go to 8, right, on the log right there, and if you plug that in, go over here. You can kind of see it, right? That really is 3 right there. So log base 2 of 8 is 3. And that is one way that you can kind of use, one thing you can use to think about how to evaluate logs. That they are just like, you can kind of think of this as 2 to something, right, is equal to 8, right? And the something right here is going to be the answer. What do you plug into the exponential function 2 to the x to get 8? Okay, it's 3. All right, so there's basically 2 ways that we think of logs. All right, one is the thing I just talked about there, that like a base b log function is the inverse to a base b exponential function, right? The other thing you can think of a log function as is an exponent. All right, an exponent, and specifically, they are the exponent that you raise the base to in order to get the input for the log, okay? So if I go over here, right, this log, when I look at that, I actually view that as an exponent. This whole thing is an exponent. It's the exponent 3, because 3 is the thing you raise 2 to and get 8, right? The log is the exponent that, so here I'll write it like this. So this is kind of the first way on that next slide that we can think of logs as an inverse just to exponentials. But you can also think of it this way. You can think, okay, 2 to the log base 2 of 8, right? These should then cancel and give you 8. So this log up here is an exponent. It's the exponent you raise the base to get the thing inside there. That is really like kind of how they cancel, just like that. Very similar to like how like the cube root of x cubed cancel and give you x, right? So just like how these cancel and give you x, these are canceling and giving you the 8, okay? This is just sort of a diagram sort of how you could think of this. So you can think if b to the x is y, okay, that's like your exponential function. Then over in your like inverse world here, the exponent up there, right, is the log base b of y, right? So you can do all sorts of things like just, I don't know, here's another one. We saw in another video that log base e of x is just this thing, natural log of x. And so you can do e to the log base e of x, right? Or ln of x, right? And that would equal x. These things would cancel. Or you can do ln of e. You can even just do ln of e, right? And that would equal 1. Because it's going to cancel off and give you the exponent that's right there, which is 1. Yeah, logs are just exponents. They're just the exponent that you raise the base to in order to get the input for the log. So just like the x right here. So I just wanted to do a few kind of conversion problems, I guess, kind of using this idea right here to help us kind of see this connection between logs and exponentials. And if you ever want to convert, the trick, the way I do it at least, is the bases have to be the same. So you can just match up the bases, and then you can just go ahead and switch inputs and outputs, right? Because they are inverses, so their inputs and outputs are going to be reversed, right? So if I was doing, if I wanted to write this first log as an exponential, I can see the base 2. So it's definitely 2, and then there's going to be an exponent, and then it's going to equal something out over here, right? And all you got to do is you got to switch the input and output. So the log base 2 of 1024 is the exponent. So this log equals the exponent. So this is now what's going in for my exponent. And then this other part, right, is what will go right here. So 1024. And true enough, 2 to the 10th is 1,200 or 1,024. So for this one, base 49, right? And then switch inputs and outputs. So 49 to the 1/2, right, is equal to 7, because it's really just saying the square root of 49 is 7, right? Switch inputs, outputs. The log base 49 of 7 is the exponent 1/2 that you raise 49 to and get 7. That's how you want to think about it. Now these ones down here, we're writing a log. So you have log base 3, right, because it's a base 3 exponential. And again, switch inputs, outputs. So we got a log base 3 of 243 should be 5. The log is always just going to equal the exponent. So, the exponent in this one is negative 2/5. So we can put negative 2/5 right there. That's what the log should equal. And I guess if you take log base 32 of 1/4, you get negative 2/5. So that's it. So, yeah, basically just match up the bases. All right. So these next problems here, I would want you to be able to do these without a calculator, using kind of what we just talked about with logs. They all actually simplify really nicely. And I'll kind of show you how I think about them, but these would be good problems to go and definitely try on your own and just see if you can get them. So honestly, some of these ones like down here look kind of scary, but I'm just sort of making it look more complicated than it is, but we'll just go in order still. And they're really all about the same kind of difficulty once you see how they work. So for this first one, conceptually you can just think about it as this log is the exponent I'm going to raise 4 to get 16, right? So it has to be 2. But another way you can kind of just see that is you can do log base 4 of 16 is 4 squared, right? And so these should cancel, and then that would equal 2, right? That's one way you can think about it. But you can also just think about it as 4 to something 2 is 16. Right? This one, log base 1/2, 256. So the way I kind of think about that is, so 256 is a power of 2, okay? It is 2 to the 8th is 256. So if I want to raise 1/2 to something and get 256, then I would just have to introduce basically a negative exponent, right? Because if I have the reciprocal of 2, which is 1/2, then I just need a negative 8 in there, and that would do it. So this one was 2, this one's negative 8, because 1/2 to the negative 8 is 256. This one, like any of these two, just so you can kind of know, like the idea is like, you're going to have to be able to, I'm not going to give you like a crazy decimal. Like if it's one you can do without a calculator, it must mean like down here, 5 to something nice is 125 times the square root of 5, right? So, a lot of times what I'll do in these problems is I'll just go and I'll think about how to write these things with base 5. So, we know 5 cubed is 125 and square root of 5 is 5 to the half. And so we also know that you can add exponents. And so this is 5 to the 3.5. Right? And so now, again, you can kind of do this trick where you cancel these things off. And we could just say this equals 3.5. That would be that one. Next one, you got to be able to do 2 to something and get the 7th root of 32 here. So on this one, 32 is a nice power of 2. So I'm also going to do, so 2 to the 5th is 72. Sorry, 32. So I'm going to put that in. And then the 7th root, we know is the 1/7 power. And we also know that you multiply exponents when you do a power of a power. So you have 2 to the 5/7, right? And then once again, do this kind of trick, cancel these out, and just get 5/7. This is actually a really nice, easy one because, we know that anything to the 0 power is 1. So if we plug in 1 to any log, the answer should always be 0, right? Basically, in words, log of anything. Oh, wait. I meant to write base anything, not of. So I'm going to add the word base. Anything of 1 is 0. That's what I want to say. And, again, that's really just comes out of exponent properties. Like anything to the 0 is 1. So for a log, anything, log base anything of 1 is 0, right? This last one looks kind of scary, but honestly, it's kind of one of the nicest ones because it's already literally set up. You're doing log base pi of pi. So go and cancel those things. And then you're literally just doing 1 to the 2 to the 3 to the 4 to the blah, 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 all up to the 99th power. And 1 to anything is 1. And so this is just 1, right? Looks kind of scary, but it's actually very straightforward. So, yeah. So, and this is kind of a general hint that I would put here. So that just like here, if you're ever doing one of these without a calculator, try and write the input for the log, so the 16 here, as the base, in this case 4, to a power. And then that your answer is the power, okay? So, we can write 256 as 1/2 to the negative 8, which is why negative 8 is the answer. Always the power is the answer. Log is an exponent. All right. So last thing I want to talk about in this video is just some stuff with domain of logs. So on the first day we studied logs, we talked about the properties of them, and there was like a really important slide where I kind of had exponential properties on the left and the inverse log properties over here. And one of the things we talked about is like, so since actually I can go back to this picture. Since exponentials are defined everywhere, right? This just keeps going like this. Since their domain is infinite, it means logs ranges are going to be infinite, right? This will decrease forever, and this will slowly go up forever. And surely they are symmetrical right there. But the exponential functions we talked about have a restricted range, right? Their range is cut off by the x-axis here. And that in turn meant that the logs are going to be cut off in that'll mean that the log is cut off in the y's. Y equals 0, but their ranges are infinite, but the domain will be just here greater than 0. And so what we can basically do, let me go over here. So we can just take that idea, and if we ever want to find the domain of a log function, we can just simply take the inside and set it greater than 0, okay? And so just like with even root functions, we had to set up and solve an inequality. To find the domain, we're going to have to do the same thing. And basically here, it's a little different. You just can't plug in a negative or 0 to a log function. Before with square roots, right, like even roots, we could take square root of 0. It's 0. That was fine. So for the even roots, right, what we did was we set it greater than or equal to 0. For logs, we're going to just set it strictly greater than 0, the inside, okay? So I'm just going to go through 3 examples, and I actually have a graph on one of them here that we'll talk about in a second. But so this first one, we just take literally 3 minus x, and we just set it greater than 0, okay? In this case, it says that this log is only defined when x is less than 0. Or less than 3, sorry. This makes sense because if you think function transformations, right, you've got a negative x in there. So, most log functions kind of look like the one over here, but we've done a horizontal flip, right? So now it's going this way. It's going that way. And there's like a shift because of the 3 in there. So that one's just x less than 3. All right. Here, you just need, again, x squared plus 5 greater than 0, right? And it's a quadratic inequality. Don't forget, whenever you get a quadratic inequality, I would highly suggest you just graph it to solve it. So we've got a quadratic that's just shifted up 5, right? And if we wanted to know when is that thing greater than 0, well, it's always greater than 0, right? And so the answer to this thing is literally all real numbers. Everything in the world would work there, which is kind of weird, but logs can do that. This last one's getting a little bit more complicated. So I'm just going to start with the top. So we need 16 minus x squared to be greater than 0, right? I'm going to move everything to the right because when I solve these quadratic inequalities, I like them positive. So if I move it over, it's going to be x squared minus 16, right? And then if I just kind of put up here x squared, so let's just say that's 16, right? So this is my x squared minus 16. Oh, sorry, should be negative 16. Then we wanted to know when is it less than 0. So less than 0 right down in here, right? The roots of this are a nice -4 and a 4, right? So so far, the domain for that top part is anything between -4 and 4, right? That would give me this stuff here that is strictly less than 0, okay? But you have a fraction, right? And you need to be careful whenever you get a fraction, you don't want to divide by 0, right? So because of that, we need log base 2 of x not to be 0, right? And literally on the last slide here, we were saying that logs are going to equal 0 anytime you plug a 1 in, right? Because of the inverse kind of idea with exponentials. If you take anything to the 0, you get 1. So log of 1 should be 0. So that is telling me another important fact, that x can't be 1, right? And then there's also, that's just the divide by 0 stuff. But we also just have a log, right? So we also need that, just because of that log there, we need x to be greater than 0, just for the same reason that I did the domain on all of these, right? So now you've got these like 3 conditions, right? And you can see that they're definitely going to affect each other, right? You basically can't have any of these negatives because x needs to be greater than 0 from the bottom, like the log on the bottom. And then x cannot be 1 also. So the final answer for that one would basically be anything between 0 and 4, but x cannot be 1. And that would literally be the domain. This is actually the picture of that if you graph it. So you can see this black line is 0, x equals 0. This one's x equals 4. And this is x equals 1. And I just put those in just so you can kind of see that it really does match up with this. But yeah, the log is sort of, because it's like a rational function, it is doing like it kind of has the structure of a rational function here. And then, this vertical asymptote is tied in with where the bottom equals 0, like we studied in rational functions. So this is just the weird picture. I'm not going to ask you to graph things like this because it's pretty hard to know like all these different things. But you do have to know how to do domain for a log. So when we get to solving equations with logs, it's going to be really important that you can do this because just like with the even roots, you'll have to know sometimes you got to chuck an answer because even though mathematically it looks like it should be part of the answer, it really isn't part of the answer.